going to say a few words to kick it off then, and for the video afterwards. So like I say, good evening. Thanks for signing up and tuning in. Obviously, a massive thank you to Dirk for being with us. So a bit of background, a bit of call for help here. For those of you that don't know me, my name is Barry Cranford. I'm the founder of the London Java community. So I'm not a developer myself. I run a tech recruitment company called RecWorks. Here at RecWorks, we've been on a mission for the last 12 years to find ways that recruitment can be a force for good in the tech industry beyond just getting people jobs. So what does that mean? Well, essentially, we create groups and platforms to connect people to help them learn, help them find mentors, and basically aid career and skills development as much as we can. And that can be on a group basis, like this evening, and through communities like the LJC, or on a one-to-one level, which is usually done through the Meet a Mentor community. As for what I could do with your help with, so we have, as part of all this mentoring, we have a new group called the Aspiring Speakers. And it's the idea is to try and launch careers of speakers, get more people out and into the conference circuit as much as possible. So every second Friday, we are running lightning talks events. We have one tomorrow. We have one so every 2 weeks. So if anybody is interested in getting involved, please come and talk to me. Look me up on LinkedIn or on the chat on here. And if you can make it tomorrow lunchtime, 12:30, then it'd be great if you could come and support the speakers of tomorrow. It's all powered by revenue from recruitment. So we're only able to do all these good things because we make placements in the Java world. So if you're looking to hire or you're looking for a role, then please do bear us in mind. Anyway, on to this evening. So tonight we've got Dirk Koenig, who works as a professor at the University for Applied Sciences and Arts in Brugg, Switzerland, and enjoys a fellowship at Karajan AG, Basel, Switzerland. He's committed to many open source projects, including Frege, Groovy, Grails, GPARS, and GroovyFX. And he's also a Java champion, a Java 1 rockstar, and the lead author of the Groovy in Action book, which is among Manning's best-selling titles of the decade. So Dirk, I'll hand over to you.
Oh, thank you very much for the kind introduction. I hope you're all well and you managed to come through the summer without any infections whatsoever. So thank you for your interest in purely functional programming on the JVM. And let's start right with this. I mean, after the, let me quickly see, how is that? Is that working? Here we go. So that's me, the least important part of the presentation this evening. And our topic is Frege. So I'm often asked how to pronounce Frege. Frege is a German name. It was a German mathematician 100 years ago, a little more than 100 years ago. And if you're English, you're entitled to call it Freaky if you want to. We are fine with that. So if you want to learn more or follow along through the slides or maybe out through the online REPL, you can go to frege-lang.org, and there you will find all kinds of information about Frege. And we will see how that works. Maybe in a few words for organization. I do have the chat window open. So if you want to kind of speed up, I'm too slow for you, then you can just ++ in the chat. I see your ++ and I will speed up. And if you think, well, wait a minute, or you want to raise a question, say minus, and I will slow down, and you can keep up with what I've done. Equals. You already got you got the idea. Thank you very much. So that's good. And if I ask like, how's everybody? And you want to say, well, I'm fine, give me a ++. So how's everybody? Hey, there we go. Not equals. Huh? This is some existentialist philosophical contribution there. Awesome. Very good. So there we go. So let's proceed with our slides. First, when we talk about purely functional programming, and functional programming has somewhat gained a strong foothold in the industry, in the software development industry, we speak of different things, and we can point out all kinds of benefits, like 1,000 hands-on immediate benefits. We can talk about benefits more on an abstract level, but I'd like to introduce functional programming more with an experiment. The idea is, how much easier is it to think about code when it's functional code? So the initial idea is that I give you a program. I just read you a program. I tell you a program, and you try to find out what it does. And then, for example, in the chat, you tell me what's the purpose of this program. Does it make sense so far? The program will have like Java-like semantics. If I say a equals 1, that means the value 1 gets assigned to the variable a. The program will have 5 lines of code and 3 variables, a, b, and c. Good so far? So let's begin. You can close your eyes, I close my eyes, and I try to figure out the program. A equals 1, B equals 2. You're with me so far? Good. C equals B. B equals A. A equals C. What do you think could be the purpose of that program? Shall I do it again? Give me a plus if I should do it again. Oh, okay, good. So here we go again. Now that you know what to expect, it's easier to follow. And I always give this my students at the very beginning. So here we go. A equals 1. B equals 2. C equals B. B equals A. A equals C. Any ideas? Swap A and B. Swaps A and B. Perfect, right? Yeah, I see it. So it's a thing that swapping 2 values A and B should be a simple task. Actually, it's a task that we give programming novices in the first week to get them going and see how things look like. So in coding. So, but it's somewhat, if you hear the code, it's surprisingly difficult for such a simple task. The solution is more difficult than the problem. And that's kind of not what we want to have. So why is that somewhat difficult? Huh? If we say it could be difficult. So let's see what happens. When I say A equals 1, in our head, we reserve a place for A, sorry. Yeah, this is in our brain, we reserve kind of place. It's place-oriented programming. And then for B, also a place, but there's still the place of A, and in your head, you have to refresh your memory for not forgetting what A is about. Well, that's what makes it difficult to reason about code, our limited capacity. And then C equals B, well, now we have to look into B. B is number 2, and that gets assigned to the place of C, so it moves over. That's what kind of happens in your code. In your head when you read you the code. Here you go. Now, it gets even more difficult when I say B equals A. We have to remember the value of A and put it in B, and now B changes its value from 2 to 1. And then last, A equals C. It would have been all so much easier if I would have named the variables better. For example, C could be temp or so. That would be much easier. So why is this somewhat a problem here? Well, first, we have 3 places, A, B, and C. Place 1, 2, and 3. And 3 places to keep in our head is not so difficult. But we have to do the 3 places at 3 different points in time. So there's time in the system. Time 1 was until we kind of set the initial state. And then we had a destructive update. B changed the value. That's a destructive update. That's the culprit that makes everything difficult to reason about code. And people are notoriously bad. So your short-term memory usually has like 5 places in it, plus minus 2. And yeah, so mine is not very good. I try to avoid this. And as soon as we have this kind of difficulty, the tool that we use to still figure out what happens in our code is the debugger, right? We already see that if you need a debugger, that's typically in places where bugs creep into our code. Yeah? So the debugger is kind of, the need for the debugger is already telling that we are in difficult waters here. So the idea is for functional programming to get away with this and make it much easier, like so. A equals 1, B equals 2. Now we call this immutable values, and we just leave it like so. Our new solution. Well, there is no mix-up. Let me quickly go one back. So let's see here, like at time B, one of the difficulties here is we have an intermediate inconsistent state. At time 2, A and B are 1 and 1. This is inconsistent, right? This should never occur. If you happen to look at the system at this point in time, it's inconsistent. You say, well, I can hide this behind a method call and it's not really visible to the outside. Doesn't help, because you might look at A at time 1 and at B at time 3 and still reading 1 and 1 inconsistently, right? So the code appears to be wrong with these kind of destructive updates. But, there you go. There are some mic open, not quite sure. So yeah, so the solution here is we never change it. We never change what we have. We call it immutable values. Friends waiting to join. Can somebody join things in? I'm not able to admit people, so. Okay, good. I hope that worked. So, but of course, well, we wanted to swap the values. How do we swap values if we never change them? Well, we just look at them differently. Like we put on glasses, like glasses that, special ones that can swap values over, but the original value never changed. It's only by putting on the glasses, this is our function metaphor. And then if I would have said A comma B equals B comma A, it would have been much easier to understand what the code is doing. And we can have all kinds of different kind of glasses. We could have glasses that only look at the first value. It's one eye is blinded, and this kind of glass is called FST for the first value. And then there's another function SMD, which only looks at the second value. And then there's functions that kind of enlarge everything. It's called map times 2, and so on. So that's the idea of functional programming. Never change any value and only putting on these glasses. And by the way, if you have many such glasses, you can kind of merge these glasses into one glass. That's what we call function composition. And that's the whole idea of functional programming. Now, if that is what we want to do, now here's your challenge. Next Monday. So from Monday on, we have no more assignments, right? Assignments make destructive updates, so we program without assignments. Okay. Now, assignments are just a special case of statements. So we can actually do away with the statements. And without statements, we don't need control structures. If you don't have statements, first A, then B, then C, you don't need any for loops or any if branches or while or whatever, no longer needed. If you don't have statements, you don't need any control structures, only expressions. So your challenge for Monday, because people say, well, I can program functionally in Java, of course. So here's your challenge. Next Monday, try to program in Java without assignments, or assign only once, let's say. But any value that already has, any variable that already has a value, no longer gets any destructive updates assignments. And no statements and no control structures. It is possible. It is, of course, possible, because in a purely functional programming language like Haskell or Frege, this is what happens. You only have expressions and no statements and no control structures. So it's possible. But it feels like difficult, huh? If you try to do this from Monday on. But we can try. Now, there's actually two ways in which you can do this. You can swallow the blue pill or the red pill. The blue pill is, we keep everything as before. You stay in your happy world of Java, or whatever language you have, which is statement-oriented and does destructive updates. But we enforce a developer discipline where we say, we don't want to use this anymore, right? We don't want to use any for loops anymore. We do everything with streams, for example. Well, you could do. And that's one way, the blue pill. And the red pill is, no, we are going for a purely functional language that doesn't even have statements and doesn't even have assignments and has no control structures, and program with this. And this is what Frege allows you to do on the JVM. So that's the second approach here. By the way, developer discipline is very difficult to hold up over a longer period of time or with more people. Now, this idea is all based on purity. So what's kind of purity in terms of pure functions here? Pure functions is the result of that function, what it evaluates to, only depends on the arguments. Given the same arguments, you'll get the same results, right? And there are no observable side effects. That's what a pure function is. And once you have a pure function, there's no more destructive updates. There's no more need for that kind of debugger of single stepping and having this kind of overriding behaviors and craziness. No longer. Right? What else can you do when you have a pure function? Let's say you can use the chat again. So here's a function, and I'd like you to find out the value. Right? The function call is a mathematical one. The cosine of 0. I typed this in, maybe it's difficult to understand when I say it. The cosine of 0. Oh, that goes private, should go to all. Cosine of 0. So what do you think is the value of that? 1. Okay, that was like 3 seconds or 4 seconds. Next question. What is the cosine of 0? Oh, that was much quicker. Somebody cached the value, right? And the idea is you kind of know that the cosine of 0 does not depend on the time of day or my time zone or the room temperature or whatever. No, it's a pure function. And therefore, I can cache the value. Meaning, once you have a pure function, you can cache the value. That's called memoization. I can defer the evaluation until tomorrow, and cosine of 0 will be 1 tomorrow as well. I can evaluate this in advance. I can learn this in school, put it in the back of my head, and then give it to you 10 years later, and it will still be the correct value. I can evaluate this concurrently. If I am in my code, I have a cosine 0 over here, and cosine 0 over here, and cosine 0 over here, I can replace all of them with the value 1. If I know that function call is pure, I can eliminate all the sub-expressions. So there's lots of opportunity for optimization once that I know that I have a pure function. Now, you're in your Java code, you run across a function. How do you know whether the function is pure? Well, here's such a function. Well, you will not be able to read this, but
Mama.
The function at the very top is org hibernate EJB3 configuration add classes to session factory parenthesis map. Okay. How would I find out whether this is pure or not? Well, I look into the implementation, and the implementation calls another function, which is line 2, configure. And then again and again and again and again and again. And at the very, very last, if I go to the very last end of that evaluation tree, I find everything's fine. It's a pure function. I can cache it. I can evaluate it lazily, concurrently, whatever. Fine. Not only is that prohibitively expensive to do, but even worse, then tomorrow your teammate makes a change anywhere in the code base, and then you have to redo all the work because you have to find out whether that piece of code is accidentally called and he produces a side effect, right? So you actually, in a normal language, you have no chance. But in a good language, you can let the type system find out. The type system will only give you a proper code. It will only compile if for your function call, you you assert that this is a pure function, and the type system will find out whether any of these other functions that make up your function is impure, and if it's impure, it will fail to compile. Since it fails to compile, you have no errors. You cannot run it, you have no runtime errors. So that's the whole idea. That's the value of having purity in your type system. That's what we're trying to do. And by the way, this is Java code, but it's the same. I have the same slide for JavaScript. I have the same slides for C++ and so on. Same thing. So with pure types, you make these implicit constraints that you sometimes have. You have implicitly, you know, cosine is a pure function, even in math, right, in your math library. But you make this constraint explicit. Where, for example, is that useful? For example, in streams, Java streams. In most of the methods, like map, filter, reduce, they assume that the code that you provide in your map, filter, reduce functions is pure. It assumes you make pure functions, especially if you're doing this with parallel, right? But if you fail to do so, it still happily compiles, it still happily runs, but then gives you wrong results. Actually, especially with parallel, you can write a random number generator that way by just making arbitrary side effects in your streams. In UI code, that's often the case that you're only allowed to touch certain elements, like UI elements, inside the UI thread, and never outside the UI thread. Whereas anything which is any kind of general purpose IO, you should never do inside the UI thread because it might fail, throw an exception, run on the exception thread, and so on. Block your UI, you don't want this. So it should always be outside the UI thread. Now, if you have a type system where you can tell, well, in this thread, you're only allowed to touch these elements and you're not allowed to do any kind of arbitrary side effect, then the type system helps you to avoid this kind of tricky errors that arise from doing things in the wrong thread. And more so if you have software transactional memories, any kinds of transactions at all, because the transaction might need to roll back, then rollback only works if you have no side effects. You cannot roll back firing the missiles, right? So sorry, we didn't want to do this. That's not how it works. So pure types really help you to avoid tricky errors, right? Not only does type systems allow you to avoid the simple errors like mistyping a method name, right? That's what every type system can do. But these kind of type systems that can catch these constraints, lets you impose constraints, they really help with tricky errors. Questions so far? Okay, let's go on. So here's an example. That's a screenshot from Eclipse, and this is Frege code. And there's a Frege plugin for Eclipse, which works as follows. Here, for example, is a software transactional memory implementation. So this kind of code, where we read a counter and we increase the value and we write back the increased value in a multi-threaded way. It's shielded from multi-threaded difficulties through the STM, software transactional memory. Now this kind of type here says you're only allowed to do software transactional memory stuff here. You're not allowed to do general purpose IO. If we validate this constraint and just do some, let's say, system out println here, println, hey, I'm a side effect, the type system immediately fails and give you immediately the error markers in your code, and if you try to compile it, the compiler will fail. And actually the error message that you don't see here says, well, you proposed that only STM is valid here, but you try to do an IO effect, input-output effect, and that's not allowed. So that's what the type system gives you. You cannot possibly invalidate these constraints. And that's kind of fun. There's also the really good type inference that come in play here, global type inference that makes it happen, but this goes a little bit beyond what we have time for today. By the way, I tried to keep this to 1 hour, even though I have slides for, I guess, 3 weeks or so. So let's try to do this. Does it make sense so far? Could you follow along until here? Does the line of argumentation make sense so far? You're kind of missing out on nice examples, but the general approach to this is that, does it make sense to you? Fine, yeah, it's good. Good so far. So less tricky errors. Now we're going to do a little bit of coding because I didn't code enough today. So I tried to do a little bit of coding. If you want to follow along, you can go to the online REPL. This is, currently I had some problems with the domain name, so therefore I had to revert to the IP address. That's 86.119.37.112:9999. And then you will see the Frege online REPL, which is also written in Frege itself. By the way, the Eclipse plugin for Frege is written in Frege. So everything that you see today is written in Frege. The Frege compiler is written in Frege. The Frege REPL is written in Frege. So that's this. We will come back to this. And I'd like to first give you a little bit of a glimpse how that code looks like, what we can do. I will just maybe me quickly, I will post this in the, quickly check here. I can post this in the chat, so you have this, right? Makes it easier to go to the REPL. Should have done this right from the beginning. There you go. So, how do you define a function? Well, in the REPL on the right-hand side on the online REPL, here is a function. The function name is times. It has two arguments, a and b. And then on the equals, after that comes the expression that makes the function implementation. And since we only have expressions, so it's an expression, a times b. So it's mathematical times here. How do we call this? We can say like times 2, 3. Note there are no parentheses here. That's just implicitly there is parentheses around this if you want to. But function definition and function application is the most common thing we do in functional programming. So it has the least amount of syntax, which is only white space. So, and that gives you a 6, right? You can ask for the type of the times function. So functions have types. And the type of the times function is, and we will see in a minute what that means, kind of crazy thing. We will come to this in a second, what it means. First step, go one step ahead. So note, we did not declare any types. This looks almost like JavaScript, whereas the type inference makes from the simple most expression to the most complex expression. Every expression will be type inferred, and the type of every expression is well known to the system and checked. We can explicitly give the types, and then what we claim to be the type will be checked again what the type inference has inferred to be the type. That's an extra check for us. There's no comma between arguments. Function application is left associative. So first, the integer 2 will be applied to the times function, returns a new thing, which then is applied 3 to. So this new thing must be a function, right? Cannot be anything else. So times 2 must be a function. Okay, let's see. How do you reference a function? Well, times 2, as we said, must be a function because we applied the argument 3 to it. So if that is a function, we can give it a name. Why not? So we can 2 times 3 should give us 6, and it does. Now, if we ask for the type of 2 times, well, we had some kind of, before we had some kind of numerical value. It worked for every numerical type, but now it only works for integers because here we already said, well, we want to use integers here because 2 is an integer. So it's no longer does 2 times work for 3.0. No. It only works for integer numbers if you start on with an integer number. Does Frege have operators overloading? You can define your own operators as in exactly like in Haskell. Overloading would not quite be the exact term for this. You can implement your own operators. You can define your own operators. That's what you can do. But you cannot really overload them. So overload would mean that you have the same operator working on different types, producing different results. No, that's not possible that way. Does it make sense so far? So it's exactly like in Haskell. Operator overloading like in C++, on C. It's more like you have operator implementations. Like you can implement operators, but you cannot override the existing implementation of an operator. So if you have an operator working plus on integer, you cannot override the plus because everything is immutable, including the operators. Okay, there you go. If you remember one thing before here, so I left some space here because first we had like times 2 and some x. Huh? So 2 times x with an argument would be times 2 and the given x. That would be like we started with. But then we left it away, right? That's kind of how it looks like. Now, you can put the x in. It's kind of grayed out here. But at any time, it's kind of based off the lambda calculus, if the last parameter in the parameter list is the last argument of your function call on the right-hand side, you can leave this away. So times 2 of x here is kind of for every value of x, it gives you a value back. Right? Whereas times 2 is something, it's a function for itself, and it applies to the whole range of what x can be. It's at once it tells you this. And this is sometimes called the point-free notation if you leave the x away, because you're not defining 2 times, if you leave the x away, you're not defining 2 times for every data point x, you're defining this for all data points at once. And that's one thing that you can do. This kind of application is sometimes called currying after Haskell Brooks Curry, the computer scientist. Sometimes it's called Schönfinkeling after Amos Schönfinkel, which was a mathematician and logician. But some people call it partial function application because you're not applying all arguments, but only a few. But actually this concept was invented by Gottlob Frege, and there it comes again. So that was in 1871. So long before computers that we had this, right? There you go. And then you can compose functions, right? Here comes function composition. Now, let's say we would have a 3 times of x and a 2 times, like before, then we could apply 2 times to the result of 3 times x. And we call this function 6 times, or just 6 for abbreviation here. Well, here's a second way of writing this. We could compose 2 times and 3 times. Here's a composition with the dot in the middle. And then this function here is a composed function. And we apply this composed function to the value x. Now, the observant listener might recognize that here we have a last argument x, and here we have a last argument x. Sorry, last parameter x and last argument x. And that means we can remove it. We can cancel it out. It's like canceling in mathematics. In fact, it's called eta reduction. But anyway, so we can actually say 6 is just 2 times composed with 3 times. And that's valid Haskell code and valid Frege code to do it this way. So if I compose 3 times and 2 times, I get a 6 times. Well, it sounds logical, huh? In fact, in high school mathematics, what you learn is 6 times 2 is 12. Okay. In high school mathematics, what you learn is that this 2 times of 3 times of x is something like, if you make it more general, f of g of x, right? Functions f and g. And there's a mathematical notation for this, for composing f and g, and you might have seen this in high school. It's called f circle g, f after g, it's often called. Right? F after G. First you imply G and then you apply F after G. And this of X, here we have F composed G, right? Or F after G. That's actually, when we had this in high school mathematics, I can still remember the day because my reaction was, this is totally useless. And now as a professor for computer science, I see this and I say, well, in functional programming, everything we do is just this. We are composing functions. That's all there is. And actually functions compose so well. You know, they're composed much better than anything that has destructive updates in it. So I'll jump over this. I'll jump over this for a minute. Now with these constraints that we have, like, where do they apply? Why do you want to have them? If you're implementing a function, implementing a method, maybe in object-oriented world, you're kind of, you would like to constrain what comes into your function. So you give types to your parameters to limit what the function can be called with, you know, your method can be called with. You're, as an implementer, you're concerned with imposing constraints on the parameters. As a consumer, as a user of a function, you're concerned with the constraints that the result might have. Is it possibly null, right? Does it throw an exception? That's all part of the result, right? That's important. And if you want to go more into this, there's a really good talk by Ruda Bjornason. It's called, we are constraining the liberties. And once you constrain these liberties, you liberate yourself when writing the code, because you can now make assumptions, right? You don't have to deal with all the crazy edge cases. If you know you get a string which is not null, then you can do more than if you know nothing. That's the idea. That really makes it much easier to write robust code. So you're communicating what you're expecting and what you're returning, what you promise to return. Here's an example. Let's say in Java, you come across a function foo that you don't know what it's doing. You just see the function foo. And you see in the type system, it takes a pair of t and u, right, under the name p, and it returns something of type t. So from the first element of the pair was of type t, and it returns something of type t. So your guess might be it might return the first of the pair, right? The first element of the pair would be an intelligent guess. Could it return null? Yes, of course. Could it throw an exception? Yes, of course. Could it throw a runtime exception? Yes, of course. Could it have an arbitrary? Could it log to the console? Yes, of course. Could it go to the database? Yes, of course. So you actually know nothing about it, you know. Whereas if you have really good constraints in your type system, like here in Frege, say we have alpha and beta or A and B, we do have a pair, that's the notation for a pair. And if we return an alpha, then you know really well what happens. First, it's a pure function, cannot possibly have a side effect. Second, the only way that this function could possibly return an alpha is returning the alpha that it gets in. It has no way of creating any other kinds of alphas. It has no access to any kind of constructor. It does know the type, but it doesn't know any constructors. So the only thing, and it cannot return a null because there is no null. So that's an important thing to know. So this constraint is so strong that you can actually infer mechanically the only possible implementation of this method. And actually there's a bot on the IRC channel for Haskell where you can give such a function signature and it spits out the only possible implementation if there's only one possible implementation. So you can be so strong, right? So anything can happen. It's only A can be returned. That's kind of so strong is your, the types tell you what you can expect. Now, when we are mixing this purely functional world with Java, and in Java, there's no constraints about side effects, right? Let's talk about Java beans. You're setting a value on a Java bean and any kind of listener may fire whatever. You have absolutely no idea what happens. Actually makes it really difficult to work with Java beans. So as soon as we try to have this purely functional world and combine it with Java because that's where we live. This is the love of our life, right? Java. And we want to use everything from Java, all the standard libraries, all the open source libraries, all our homegrown libraries, the code that we already have and love. So we need to interoperate with Java. But we want to do this in a safe way. And if you just mix arbitrarily, you get no safety. If we would allow Frege code to just call any Java code without protection, then we would gain no benefits at all. And this is actually what all other languages except Frege on the JVM are doing. Even the functional ones, in particular the functional ones, they just allow you to call into Java code without any protection. And this undermines all guarantees that you would otherwise get from the language. And how often do you call in Java? Like every second line, you're calling a println, whatever. So this is really important. The way that Frege does this is when you call from Java to Frege, this is kind of a no issue because Frege compiles to Java source code and Java can just call into the source code. There is no question here. And actually you can look into the Java code that Frege produces by just giving a Java command in the console and it will give you the respective code. Here comes the more involved thing. And because your Java code might be pure or it might be impure. Let's look into a pure function. Also Java has pure functions, right? For example, the code javanet URL encoder encode. You give it a string and this encodes, all the blanks will be %20 something and so on. It makes a string that you can use in a URL from an arbitrary string. That's what the encode method does. And it's a pure function. So you can tell in Frege code, this Java function here is a pure function. It's a native function that I want. I will call it encode. That's the way that I want to call it. And then you can call encode der König and it will encode it. Fine, right? And everything with pure functions still works perfectly in our Frege world. What about a function in a method in Java that's impure? For example, Java lang system current time millis. It gives me a different value every time I call it. So it's impure. So if I want to include this in my code as, let's say, millis, I have to tell it, well, you can already tell here, it has no parameters. In a method that has no parameters, if it was pure, could only give you one value back, a constant value, right? Because for the same argument, it must return the same value if it was pure. So this one's impure. And I tell it by the type. This type here tells you it is an IO dependent activity. It's an action. And if you want, you cannot just call millis arbitrarily. So runtime exceptions are also handled by monads. I say yes for the sake of brevity, but there's different ways in which you can handle this. First, if you possibly have an exception, Java lang current time millis, I don't think it throws an exception. Even system.println doesn't throw an exception, even though it should throw IO exception if it was properly designed. Anyway, so this does not throw an exception. If it threw an exception, you can tell here, and then what you would return is either an IO long or an exception. And the caller of the result value must provide for both possible values, for both possible types, it must provide a handling method, right? That's one way of handling exceptions here. Exceptions are a little more involved, but yes, thanks for the question here. So you cannot, this does not compile. You cannot just call millis and then do some arithmetic with it. No, because the return type is not a long, it's an IO long, meaning it is an action that when performed will return you a long. It's kind of like a promise in Java, right? So you yourself can only use this if you yourself are an IO action. And by the way, the main function of every application is somewhat IO dependent, because you want to do something with your computer, right? So in IO, you must go into the IO context before you can read the value. And only there you have it. That brings us to this point in, I've just come over this. So you can call into Java, but it's always protected. That's the important point here. So the guarantees that the language gives you even apply to Java code that you call from Frege. It's a very important distinction. Frege is the only language on the JVM that gives you this. By the way, the approach of having this also appears in other places. For example, PureScript, which is a Haskell for JavaScript, follows this route. If you go, if I'm not totally mistaken, Dart also goes this way. And there's different other languages that have this kind of characteristic, but not on the JVM. On the JVM, Frege is the only one. Yeah, I'll jump over this. So what you have in the very end is your that's kind of call stack. Here's your main function, runs until end, and then your call stack. It's things are mutable and messy and dirty. It does I/O, whatever. Yeah, it reads from the file system. It writes to the file system, goes to the database, all the dirty stuff. But within the dirty stuff, you might have things that are just mutable that don't do the side effects. And then in between, you have your computations, the islands of purity. So these are kind of the colors should suggest that this is clean and fresh and like mint. And then it gets increasingly dirty the more you go to the main function, right? So that's your point. But still, it provides much of benefit, because once when you look into errors, you already know where to look for the errors in the mutable part, in the IO dependent part. Here, there's lots of errors that cannot possibly occur. Keep the mess out. Yeah, thread safe by design, and so on. So then comes the monad value over there. I'm not going into this. I'm not going into the type inference so much, but here people always talk about type inference, especially now also in Java. This here, we call it global type inference. Everything is type inferred. And this is kind of a totally different meaning of what type inference means in other languages, where you can just, where it's more convenience features for typing less. So I'd like to, we're kind of 5 minutes before 1 hour is up. We could do a little bit of programming in the REPL and show you how programming in Frege actually looks like, or we can just go through the final slides and then stop. Would you rather like to see me programming? That will take like 15 minutes or so, and then we are kind of extending the deadline by that time. Coding, give me ++, everybody who wants to see me fail in coding. That's good. So I see it. So from now on, it's your fault. Very good. There we go. Also, let's go to the browser. So I'm in the Frege online REPL. By the way, can you see this? Give me ++ if you can see the REPL at the moment. Is it readable? Okay, very good. So on the left-hand side, you do have an editor where you have, if you have more lines of code that you would like evaluate at once, you can use this. On the other side, there's a line-by-line REPL. And what I'd like to program with you interactively is the FizzBuzz challenge. So FizzBuzz is sometimes used in developer interviews. It goes like so. You write to the console all the numbers 0 or 1 to 100, and every third number, you should say fizz, and every fifth number, you should say buzz. And if a third and a fifth number is both at the same place, then you should say FizzBuzz. Otherwise, you say the number. So it goes like 1, 2, fizz, 4, buzz, fizz, and so on, right? That's what you're trying to do. And we're trying to implement this interactively in Frege. Clear so far? Okay, good. So first, how do we put out numbers? Well, this is the open bracket, close bracket. It's the syntax for a list. And we can start with 1 to 100, would give us the numbers from 1 to 100. But we can also, it's even nicer, leave away the right border, and we get all numbers, all integer numbers. Now, since this is evaluated lazily, the REPL can be intelligent enough for not putting out all numbers, but only enough numbers that we can work with, right? Until we reach the visible end here. So that's one thing that you can do with lazy evaluation. But we don't want to use the numbers here. We'd like to do the numbers as strings. So we are mapping over it. We give the map function. We are mapping the toString of the number over it, right? ToString in Haskell and Frege is called show. Show is a function that at this point will be applied to a number. Number has a show function that will produce a string. Here we go, 1, 2, 3. So we have, and now that we have an expression that gives us all the numbers as strings, we can give this expression a name, and we call this name nums, let's say. Nums, you can say it looks like a variable, but it's like a function definition that has no parameters, and therefore can only have one value, and this is the value. The value is the whole list of strings that happen to contain numbers. Good. We also see what the type is. So it is of type list of string. That's how you read this. Now, we also need some kind of notion of every third is fizz, right? And one way of encoding this is, well, we give it an empty string and another empty string and a string that's called fizz. So this would be a list of three strings. Now, in a lazy language like Haskell and Frege, we can produce an endless repetition of a list. And that's a function that does this from a list to an endless repetition of the list is called cycle. We're cycling through the list, right? And now we have an endless production of empty, empty fizz, empty, empty fizz, empty, empty fizz, and so on until eternity. And we can give this a name. Let's say these are the fizzes. Huh? Let's say, good, list of string. As you can guess, we do the exact same thing for the buzzes. Buzzes, cycle, empty, 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 comma, buzz. Now, let's say how the buzzes look like. Buzzes, yeah, there we go. Every fifth is a buzz. Now I'd like to combine the fizzes and the buzzes. It's all about function composition. Now I'd like to produce an endless repetition with this pattern of every third is a fizz, every fifth is a buzz, and every 15th is FizzBuzz, right? How do we do this? Well, combining two of these lists is called a zipper because it works like a zipper on your jacket, right? There's two lists, and then pairwise we assemble them like zipping. That's called zip. And we do the fizzes and the buzzes. Well, this produces a list of pairs. Okay. Pair is not quite what we want. We'd like to have a single string. But note, if we just append these two strings, we get exactly what we want, because appending an empty string does nothing, happily. So we would like to do this zipping, but apply a function here when combining each element. So the function that does this is called zipWidth. And now here, we can give a function that for every pair of elements returns a value. So let's make a function, an anonymous function that takes an argument from the string from the fizzes and a string from the buzzes, and it returns f concatenated, so it's double plus b. And this is double plus is concatenation on strings. So let's try. Aha, that looks good. Fizz, 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 buzz, 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 fizz, FizzBuzz, and at position 15. That's good. Now we can improve this, right? Now what we now do is we work with our code like we do in mathematics with a mathematical set of equations. Actually, your code is a set of equations. Your code becomes an algebra, and you work with the same confidence on the algebra as you do in mathematics. Well, this is so cool. And my students always laugh when I say, now your code becomes an algebra, what could be better than this? And then I often have to explain algebra for the first time to them, because the algebra is really cool. So your code is an algebra, and we make equality translations. So like refactorings, you might say. So this is an operator, plus plus. It's a binary operator. And we can make a binary operator into a function by putting it in parentheses and then give it the two arguments. So that's the exact same thing as above, but we are changing the notation, right? This is the plus plus function, and we apply it to f and b. Okay, see whether it still works. Yeah, still works. Now, this is an expression, huh? And here the last parameter of the expression is the last argument to this function. So what can we do? And this is with mathematical rigidity. Well, that's part of the lambda calculus. We do an eta reduction. We cancel out the b. We are returning a function. We cancel out the b. So our function is a function that only takes an f, right? So kind of a partially applied function as we had before. Does that still work? We are kind of mechanically apply what we have learned. And actually an IDE could do this and it's all based on purity. Without purity, it wouldn't work. So still works, huh? Now, can you see here, there's an f and there's an f. The f is the last parameter in the formal parameter list, and the f is the last argument to the plus plus function. So what can we do? You got it right. We can remove the f. And then we remove the whole parameter list because there's no more parameters. And then we can remove the superfluous parentheses. So we are zipping the fizzes and the buzzes with the plus plus function. Does it still work? Hooray! Huh? Now, by simply applying these rules that actually an IDE could do without the slightest possibility of errors, right? Any kind of refactoring that you are reducing, there you go. Almost reducing. We're kind of expanding instead of reducing, but yeah, there you go. We can also, you mean reducing the f? Yeah, that's true. Any refactoring that you do in your IDE somewhat only happens by chance. There's always exceptions to the rules, right? With this kind of language, in IDE could actually give you 100% total safe refactorings. I'm still waiting for the IDE vendors to understand this, right? Yeah, I'm talking to, it's difficult to get this across to the IDE vendors. Anyway, so we now have the FizzBuzzes. We can give this a name. We call this, let's call this the pattern. Right? And this is our pattern. So pattern, if we call this FizzBuzz, there you go. Now we have to combine the pattern with the numbers that we defined. Remember, we have the nums. Now, how do we combine the pattern and the nums? Any zip? You're done, you know? This, you already know Frege and Haskell at the same time. You learned Frege, you already learned Haskell without even knowing. So here we go. Zip, nums and pattern. We get these pairs again. Huh? So going to zip with and create a function. The function gets an n from the nums and a p from the patterns. So let's see. If the pattern is equal to empty string, let's get an if here, then, well, then we should do the number, right? If for the first time pattern is the empty string, then we should do the number here. So then n, else we use the pattern. If we have a pattern, we use the pattern, huh? Else p. There you go. Like almost done here, right? We are almost done. We now have an endless production of this thing. We can actually call this, let's say, I have to go here, give this a name. I call this the FizzBuzz. Okay, and FizzBuzz is this. We can start at any point. We can say first drop 100 from FizzBuzz and then take only 5, right? So drop, just drop so many elements and then we take the first 5. So we should get 101 fizz and so on. So that's actually pretty cool. 105 is FizzBuzz. Yeah, true, because it's multiple of 15. Yeah, there you go. Now we're kind of much better than usual FizzBuzz. But we're not quite there because we only have evaluated the list that we want to have, but we didn't print this to the console. We'd like to print this, right? We'd like to kind of iterate over the FizzBuzz and then print it. Let's say take the first 16, huh? And then do the FizzBuzz. Well, what we would like to do with every element here, we would like to do a println with this. So here we have strings. We have a list of strings, and if we println the string, then it will print it to the console, right? So applying something to every element is a mapping. So if we could map this, right? That would be our approach. Could we map the println function to every element for printing it? It will not work, but let's try. Let's see what happens. This evaluates to a list of IO actions that return no value, that return an empty value, right? We have a list of IO actions. We computed a list of actions. But we kind of execute the action here, right? There's actually a special variant of the map function that not only produces these actions, but also executes these actions. It's called mapm. That's a monetic mapping. And that's actually the variant that we need here is as an additional underscore. The underscore means we have no interest in the result value. We don't care about the result value, and you can forget the result values of our actions. So this would now give us all the values here. So that's nice, but this looks kind of crazy. Huh? Actually, that's kind of, what would be much nicer if we had a function that we can use here instead of mapm, which is kind of technical, it's a technical term here, but we would like to have some kind of nicer function that would take a list of something and then have some kind of list or iterator or whatever, and then puts it into a function, like say the println function. And if we had this functionality, this would look like a for loop, right? We have a for loop going over the FizzBuzz, and then for every element in the for loop, we put it into the println. Huh? That would be nice. How would you call such a function? If you would be the language designer of Frege, how would you call that function? Lift could be, for each could be, for each would also make total sense. Apply could be, yeah. Actually, all these names have already other meanings in Haskell and Frege terms, but actually the function here is for, right? That's actually for, the definition of for is just mapm with the arguments switched around. So the code that produces this is for text 16 FizzBuzz println. So we have pretty much used the 15 minutes. But by the way, if you're playing with these with the online REPL, it's pretty nice to go to the walkthrough examples. They are listed from over here. If you go there, you will find lots of examples that are interesting to use and understand characteristics of the language by trying them out in the REPL. And it goes beyond some, and then there's even some, how do you make data structures and how do classes and so on, and instances of the type classes, and how to construct a JSON from these and so on. So it's actually, it goes into a really usable code here. It's interesting to use. But let's finish off with the presentation. Here we go, FizzBuzz. There's a lengthy description about FizzBuzz, and it's linked from the Frege homepage. There's a Git book that explains you lots of interesting characteristics about Frege, and also helps you as a Java programmer to understand why people are so enthusiastic about Haskell, and you can use this kind of programming with Frege on the JVM. That's the idea. And this Git book gives you lots of interesting examples. So let's go over the FizzBuzz. So when you look up FizzBuzz in Google, is there a particular way to write unit tests in Frege and set on expectation of your expressions? Yes, there is, so-called quick test. Haskell has quick test and Frege has quick test. It's very much like JUnit 5 now has become, right? Property-based testing in JUnit 5, including the shrinking and so on. So Haskell has this since 25 years and Frege has it since 10 years or so. And I'll come to this in a minute. But testing is awesome. You know, testing is so much easier if you have pure functions. So much easier to create your test fixture and make really good unit tests. We'll come to this in a second. Thanks for the question. So if you Google for FizzBuzz, at least that was the first hit, the most prominent hit on Google when I tried it. this is your, it comes on with this kind of Java code. I'm not bitching on Java here. So it's actually this would be the same in most object-oriented procedural languages. And of course, this code is bad, right? But let's see why it's bad. So here is our FizzBuzz as code in lines of code. Huh? This, I mean, this is a slight variant of what I've done with the best of function, but that's pretty much what we have said so far. Good. If you compare these two approaches, then for the imperative way, how many conditionals do you have, right? So here is conditionals, here is conditionals. Actually, you have to be really careful with your conditionals. Yeah, here's conditionals, here's conditionals. I don't know about you, but I keep track of the programming errors that I do. And for a very long time, all the programming errors that I did, or most of them were about conditionals. Too many operators in too many conditionals. And then there is where bugs hide, right? So if you can avoid conditionals, that's always good. So let's go back one slide. So there's 4 conditionals in the imperative variant. In the logical, the Frege, no conditional at all. You can, the equals conditional for the final one is one that you could count if you want. So you might argue for there's 1 conditional. Okay, I give you that. How many operators? There's 7 operators and there's 1 operator in the logical version. The nesting level for the if else is 3. There's no nesting level whatsoever in the logical function. These characteristics here always increase the likelihood of errors massively, right? Conditionals, how many operators, how deep the nesting level, you will get it wrong. But most importantly, here comes the most important point. With this approach, you have to be extremely careful, right? You first have to check for the 15 or the divisible by 3 and by 5, right? And only then do you check for 3 and for 5. Here the sequence is identical. You could check for 5 first and 3 second. That would be okay. And only at the very last you do the you do the case for the number. So it's very important that you get the sequence right. Whereas here, any sequence of the code is equally correct. You can swap the lines around to your liking. Well, all of them are correct. Now, if you have 4 conditionals and you have to get them in the right order, there is 4 faculty 4 combinations. That's 24, and only 2 are correct. Your chance is 2 of 24. And here, every single one is correct. So now let's say, here comes the maintainability, right? Here, what do we have to change in maintainability? There comes your boss and says, well, now every 7th number should be London Jug. Okay, what do I have to check? Well, I have to check for divisible by 3 and 4, 3 and 5 and 7. And 5 and 7, and 5 and 3. And then you try to implement this, and then you recognize you have forgotten one of the many combinations, right? So it gets prohibitively difficult to keep the code correct. Whereas in the logical version, there's another pattern that you apply, period, right? How difficult can that be? So it's much easier to keep the correctness when changing code. But here comes the kicker. Here comes really the kicker. If you go, that's most important to me and the most difficult to convey when I talk about code. When you start here and you start incrementally, let's say first you're only concerned with number 3. and then you implement for number 5. And then you implement for the combination of those. So anytime you make a change, you have to recompile everything, and you have to touch kind of the whole code base, and you might possibly introduce errors because you compile everything. Right? So there's no really incremental development here, because you have to change everything. You don't work in increments. You're making small changes, but that changes the whole structure. See what I mean? That's what makes it so difficult here. You have to understand the whole program for making a change. It's the second thing. Now here, we started with the numbers. Did we touch the numbers after we introduced a new pattern? No, right? Like every single line of code here is its own module. We never went back and changed an old module. We worked in increments. For every next line, we didn't need to change the lines before. And this is important for incremental development. You can define an increment without touching the old code, not even recompiling the old code if you don't want to. If you don't touch it, if you don't compile it, what can you break? Nothing, right? This is important. Actually, that's kind of not well enough understood technical prerequisite for agile development. If you want to do agile development, you need to have a system that you can work incrementally. And that means you can make an increment without touching the old code. So the best thing that we can do in most languages is having a test case that kind of gives us confidence that we haven't broken anything. But it's better if you cannot possibly break anything. Right? See the point? That's big. Yeah? For me, that's one of the characteristics of this kind of programming that is vastly undermarketed. There you go. Here is the quick check thing. Quick check is the testing facility. Here, for example, you produce, you're working with invariants. You have invariants like, let's say you have an AVL tree, the kind of balanced tree, and a tree that has a certain kind of balance between the depth of its nodes. And here you see, then you provide functions that gives you invariants for your tree, for your data structure. For example, the difference between the tree balance for any node can be at most 0. There is no difference in height between any kind of node that is bigger than 2, not 0, right? So you can have these kinds of constraints again, but now constraints as a test case, specific for your application. And then automatically, Frege QuickCheck knows how to produce these kind of trees because it looks into the constructor. Randomly creates all kinds of trees and then checks whether your invariant still holds. That's actually pretty cool. It's very close to what Java 5 and property-based testing now in JUnit 5 is doing. That's cool. Let's jump over this. For finishing up, what is unique in Frege as the language, as in Haskell for the JVM? It has global type inference, which only works if we have purity, and it is the only language on the JVM that has this. It has purity by default. So if you do not give any kind of indication that there might be IO involved or any kind of external force here, then everything is assumed to be pure. And if it's not, you get a type error, right? Effects are explicit in the type system. This is the only language on the JVM that has this kind of characteristic. You get type-safe concurrency and parallelism. That's the only language on the JVM that has this. It has laziness by default. We used it in the REPL. It's the only language on the JVM that has this. Others have special kind of data structures that are lazy, but here's the only one. For example, the lists of strings that we have worked with in the FizzBuzz example, they look like lists, they feel like lists, you manipulate them like lists, but they're actually lazy lists. So every element gets produced when it needs to be evaluated. And actually that makes a list work more like an iterator. Actually, they're from a Java perspective, they are more like a stream or like an iterator. But it's easy to forget because you think in terms of lists and it's still efficient. This is about efficiency here. All values are always immutable without exceptions. There is no exception to this rule. It's the only language on the JVM that has these characteristics. And these guarantees extend even into your Java calls. Even if you use Java, because of the guard that you have before the call, these guarantees extend into your calls. So not only is Frege the only language that has the combination of all these characteristics, it is for either one of these, it's the only one that has this characteristic. And that's kind of an achievement of its own. This gives you robustness, right? In all kind of ways. It allows you for equational reasoning. Your code becomes a set of equations. And that's somewhat the best way to learn functional programming, I would say, because you cannot possibly go shortcuts here. It enables incremental development that way, and it allows you, because it runs on the JVM, to use it in your daily life, in your daily work as a Java programmer. You can sneak it in. It produces Java source code, so nobody can tell the difference, even though the Java source code doesn't look like handwritten. But for me, it is actually about learning. Using the language and going this route of and being forced to do the purely functional programming expanded my knowledge of programming vastly. And it actually changed my approach to many program problems, because now, when first I thought, I used to think, what kind of object do I need? What kind of class do I need? What kind of dependency and they need, and so on. And now I think, okay, this problem is a function from what to what, right? And this is it helps me in many, many ways. Investment in knowledge always pays the best interest. It's actually at least once a week when working with Frege, at least once a week, sometimes more often, I end the day knowing that I have understood something about programming that I didn't know before. And I do commercial programming since over 30 years. I've seen lots of code. I did many errors, and it's my considered opinion that these kinds of languages are the future. This is where there is a huge potential of improving our trade. Yeah, so we have, we can tap into the community of Haskell. We can tap into the community of Java, awesome community. It kind of combines the two. It's pretty popular on GitHub. We have over 3,300 stars, possibly 3,400 now. There is 26,000 Haskell projects on GitHub. We are in the top 10. The top 10, not in the top 10% or so, we're in the top 10 projects, right? Number 8 or 9, I guess, at the moment. So that's pretty remarkable. But also there is 1 million Java projects, and we're in the top 0.03% in terms of GitHub stars. Right? So progress in the project itself is usually slow. We take our time. We don't need to rush. We want to do things right, better than fast. We don't want to be fast at the expense of being correct. So we are in there for the long run, for the long game, let's say. That is our approach. There's lots of tools around, especially all the Maven, Gradle, and so on. There are some interesting editors and IDE support things going on. There's training material. You can pretty much use all the training material from Haskell and apply it almost one-to-one. For some of the Haskell books, there is translations of the examples to Frege if you want, for at least 4 or 5. And there's, of course, the scientific papers and there's special training available if you want to have that. Lectures, videos, and so on. That's me. And we can go into final questions for wrapping it up. Is everybody exhausted or? So we have like 21. What sort of problems does Frege target? So actually, what can you do in Frege? Everything that you can do in Java, you can do in Frege. But there's certain aspects where you really profit from the purity. And this is especially when it comes to, you want to impose the constraint of purity. And this is particularly helpful with software transactional memory. This is very helpful for UI-related work, like with FregeFX, where you want to make sure that you touch JavaFX elements only in the UI thread and do all the other stuff outside the UI thread. We did, if you go, let me quickly see, into the Frege.org. Frege-lang.org. I have to, there you go. So at the very end, there is related projects. So there's some projects, for example, the compiler of Frege is written in Frege, and many other compilers are written in Haskell. Writing compilers is a really good thing with a purely functional language. And by the way, the Frege compiler is really efficient, right, as compared to other languages. So it's actually pretty cool. And the Frege compiler itself is written in Frege, as I said. Then there's a ray tracer written. That's also a pretty cool thing. A ray tracer in Frege. Frege Chat is an implementation that I wrote for the upcoming language bowl, where it's kind of a competition between upcoming languages, emerging languages for Java 1, where Frege did win. There's a parser library written at the University of Düsseldorf. There's Conduit. Actually, I just last semester, I had a master's student who used Frege with Apache Spark. So this kind of big data analysis, scientific data analysis that you can do with Apache Spark profits from the knowledge of having your functions, your reduce functions, in particular your mapping and reduce functions, being pure and being guaranteed that they're pure. So that also helps, right? So it's these kind of data science applications is really nice. And there's tons of examples also in the code base for Frege with all kinds of interesting, crazy logical programming. That's also nice, I would say. I'm not quite sure whether this answers the question where it's actually best used for. I actually like to use this kind of approach with user interfaces, mainly because I do lots of work in user interfaces, and making sure that I'm in the correct thread and I can reason about my code in user interfaces is really big, you know, because user interface code is notorious for getting messy. And having this kind of constraint really keeps the train of thought in place. That's cool. Frege or Python? Now Python is kind of the opposite spectrum of languages, right? In terms that Python, even though there's a certain way of using comments to make Python somewhat type-safe. The idea of type-safe is being interactive, like we have been in the REPL, but without any type constraints, right? I was distracted by work for a bit in the middle. Did you cover calling Frege function from Java? Yes. That's actually no issue. Frege compiles to Java. If you want to call these functions from Java, you just call the respective method. Yep. Fish. So I don't really know the word fishitis. I hope it is not derogatory. Thank you very much. Yeah. So, kidding. I'll say. I see the point. Thank you very much. I learned something. I learned a new way. I learned a new word. So awesome. Thank you very much. Please give it a try. Let us know any kind of difficulties that you stumble across, any kind of wishes that you have. It's all on GitHub. It's all open source. It's all, what is it, BSD license.